Welcome to Klein's Geometry. We're going to talk today about algebraic proof, lesson 2.5. For a complete list of all of the postulates we've got there and the properties, we can go to page 104, see them all. You've used them all, though, so you know them. Don't panic when you see the big list. Here's what we've got. We justify what we've done to find answers to math problems using properties of equality. Your algebra teacher probably told you these when he was explaining or she was explaining how to solve equations, but you were so focused on the process you didn't really think about what properties we were using. We also justify conclusions for our proofs of some geometric figures using properties of congruence. And we're going to look at those. That list is on page 106. Here's an example of combining everything that we've done so far. Let's say we're given something that looks like this, a nice segment, A to C. And it's got B, which is between A and C. So, and we're given these expressions for the lengths of each of them. Now, we want to find A to B, B to C, and A to C. That's our goal. So how do we do this? Well, we use our algebraic properties. So we start by looking at what we're given. We always start with what we're given. And we say, what is the relationship between this expression, this expression, this expression, or this segment, and this segment? Well, these are clearly not equal. But what I do know is if I took A to B plus B to C, this plus this, it would equal A to C. You know that by looking at it, but it's also a postulate. And since these are segments and we're adding, it's the segment addition postulate. So that's our reason that we can write this. And as we do these things now, we always need to write what we know and put the reason across from it. So now, if I want to go ahead and find these lengths, I know that A to B is 2x, B to C is 3x minus 9, and A to C is 4x minus 4. And I can write this equation based on this one because what I just did was I used the substitution property of equality. And I'm going to just abbreviate property of equality, POE. You can do that also. I substituted expressions that were equivalent to these segments. Now, if I was going to solve this, if you were going to solve this in an algebra class, you know that the next thing you would do would be to simplify. You would add your like terms and get 5x minus 9 equals 4x minus 4. And because all you did was simplify, we'll just write simplify. You can write combined like terms, but why would you write all those words if you could just write simplify? Now, I need to get all my x's on one side of the equation, so I'm going to take 4x away from both sides. And I took the 4x away because it's smaller than 5x, and I like to have a positive x term. So that becomes a 0, and I have x minus 9 equals negative 4. You call it 1x, but x and 1x mean the same thing, so we're good with that. And what I just did was subtract, so that's my subtraction property of equality. Now I still don't know what x is, so to get it alone I need to do the opposite here. So I'm going to add 9 to both sides, and that will give me, right here you see another 0, so I've got x equal to 9 minus 4, which is 5. And I did that using the addition property of equality. Now, if I had multiplied both sides by something, that would be my multiplication property. If I divided both sides of the equal sign by something, that's my division property of equality. So all of these steps we take, we just call them properties of equality, POE. Okay? Now I want to find AB, BC, and AC, so I'm not done yet, but I know A to B is actually equivalent to 2x, So I'm going to say 2x, which is 2 times 5. So this was, and the reason I can say it's equal to 2x, that's given. And this is substitution again. I just substituted what I knew, the substitution property of equality. And that equals 10. And if you had to give a reason for this, you'd say you simplified. Now b to c equals 3x minus 9. So I can put in 5 here. And 15 minus 9 is going to be 6. And again, given, substitution, and I simplified. And finally, to get, I better come over here a minute, to get a to c, that was equal to 4x minus 4. And I'm going to call that 4 times 5 minus 4. And that's 20 minus 4, which is 16. Again, given, substitution, and simplify. So I know a to b is 10, b to c is 6, and you see when you add 10 and 6 you get 16, which you should, because if this is 10 and this is 6, this is clearly going to be 16. So then you know you did it right. So that's an example of writing an algebraic proof. You're going to put what you know on in one column, and the reason you know it in the other. What you know, why you can do it. What you got, why you could do it. What you did, why you could do it. What you did, why you could do it. That's how it all works out, and then the same thing for this part. Now the only thing I've got left to talk to you about are properties of congruence. And let's look a minute. Oh, it doesn't fit on there. Let's see if we can just make our screen a little bit smaller. Whoops, wrong way. Always goes the wrong way with me. Okay. Reflexive property of congruence. I guess that's not going to fit on here, so let's come over here and let's say I've got a segment A to B. I've got another segment B to C. And I've got a third segment. Whoa. Shouldn't have the same same letter for 2 endpoints. So C to D and E to F. Okay? So I got 3 segments here. By the reflexive property of congruence, what I can say, if I look at AB, that's a segment AB, I can say segment AB is congruent to segment AB. I know it's equal to itself, congruent to itself, same thing. And nobody could argue with that. And we get that idea of reflexive property. It's like looking in the mirror, reflecting. You got the same thing on both sides of your congruent symbol. We have reflexive properties of equality too, if you were to say something like 3 equals 6 halves. It's really the same value on each side of the equal sign. So reflexive property of equality with the equal sign, same, or you might have 3 equals 3. Reflexive property of congruent, when you have the same thing on each side of a congruent symbol. Symmetric property, let's say I know AB, that segment, is congruent to CD. Okay? So I could say, hey, guess what? Segment AB is congruent to CD. And you might say, really? Is segment CD congruent to segment AB? Well, all you did was flip around what was on either side of the congruent symbol. We still have the same statement. We still have 2 congruent things. We just turned around, which was on the right, which was on the left. Symmetric, flip it around. Symmetric, so flip it. Okay? Now, what if I went a little bit further and I said to you, guess what? Segment AB is congruent to CD, and furthermore, segment CD is congruent to segment EF. Well, what could we conclude from this? Well, if I know these 2 are congruent, and I know these 2 are congruent, I've got a link here. It's a lot like the law of syllogism. Since this one's been stated in both of them, I can say then segment AB is congruent to segment EF. Notice you take out the link, same, and you put together what's left. And that's the transitive property. I think of that transitive, sorry about that, as like a train. Transitive is like a train. We've got the cars and they link. So here's my link and here's the two end cars. Transitive has a link, and what's the same in both of these, you cross out what's left, has to be congruent also. So in summary, transitive, linking property, symmetric. You can say it either way, flip it around, both ways, it's the same. Reflexive is like looking in a mirror, same thing on both sides. And all of our properties of equality are just name the things you do. If you add something to both sides, addition properties. Subtract something from both sides, subtraction properties, and so on and so forth. But whatever you do, you must give me the reason that you do it. Justify your actions. That is how life works. So enjoy the mathematics, and I'll see you next time.